Recorded.
Okay, thank you for the introduction. Yes, so I run BM29 with Petra and Hayden. So we've already had talks from Narayan and Idea 2 and on the double beamlines about SAXS, so I won't go into any SAXS theory. They're on YouTube if you want to learn about that. What I will talk about is why we're doing BioSAXS, our Beamline, our sample environments, and our software to actually help this create a high throughput Beamline, and then a little bit about what we're going to do in the future to the Beamline. So, what I'll start with is why do we need a high throughput BioSAXS Beamline? In BioSAXS, we predominantly measure proteins or DNAs or RNAs. And in solution, which is obviously a more natural state than with macrocrystallography or cryo-EM. And we can determine the size, shape, volume, molecular weight, or flexibility within the systems that we study. And we can study samples that cannot be crystallized or are too flexible for cryo-EM. But we are limited a little bit in resolution to about 8 to 10 angstroms. Where BioSAXS excels is when it's used in conjunction with other techniques, with crystallography, for instance, because we can measure these multi-domain proteins. So we could take the crystal structure from one domain and then model it within another larger domain. So we can actually look at more full-length proteins where there may be some flexibility in the system. We can measure like changes in conformational state. So here we have the difference between, this is actually GPCR, and we've added a ligand, and so we can actually see a change in the SAXS curve when we actually, on the addition of this ligand. We often look at flexible domains, intrinsically disordered proteins, which have no natural structures. And we're doing a lot more looking at liquid phase separation, so as a protein forms into a condensate. And we've been known for many years for our blobs or our bead models. Fortunately, this time has now passed. So with AlphaFold, we can now create a model of a protein, but the question is now, is that AlphaFold model correct? So the easiest way to validate that is with SAXS. So we can just back calculate a SAXS curve and then fit that to the measured data, and we can do that in seconds. But I'll talk a little bit about that later on in our future perspectives. So why do we need to be high throughput? You may ask. Well, this allows us to measure either many different samples within a day, but also to measure maybe the same sample but many times in different conditions, such as different concentrations or different temperatures, salt, iron levels, or even different pHs. This will then enable us to characterize proteins and their structural changes within many different conditions. So to our beamline, so this is our optic switch. Now we generally just run at 12.5 keV, so that's just under 1 angstrom. We have a double multi-layer monochromator and just one focusing optic. This is a 1.1 meter long toroidal mirror. Our experimental hutch, as you'll see, is actually, one thing you must notice first is we're all in vacuum. So everything, the sample and everything will be in vacuum. Our detector is a Pilatus 32M, again, in vacuum. Our capillary, where the sample goes through, is in vacuum. And you can see here, there's a camera shining down, and here is the camera footage of the capillary. We have two main sample environments. This is our sample changer and our HPLC again, and these are essentially static in place. So we have a static, so sample detector our sample detector is static at about 2.8 meters, and our flux is about 10 to 13 at the sample, with about 200 by 100 micron beam at the sample position. This gives us a Q range of about 2.5 to 6 nanometers. Having this setup as it is means that we can be very high throughput, because we get new user groups every day, and often these user groups are very inexperienced. Some have never been to a synchrotron before. So this allows us to set up the beam very quickly, because we don't need to change in and out our sample environments. And then that gives more time to explain to the users how to use the Beamline and how best to get good data from their experiments that we're running. So this is our sample exchange unit. So this is the SEU2A. You can see it's set in here in place. And if you look inside, we have the camera pointing down, and we have a quartz capillary that goes through here. And this is a 1 mil quartz capillary. And at a later date, we may put some UV or some other spectroscopy across this designed with future capabilities. This sample exchange robot was originally developed at the BM29 with help from EMBL Grenoble, and is now actually found in P12 in Hamburg and B21 Diamond. We require about 10 to 100 microliters of sample, and we can put the sample within PCR strips or Eppendorfs or a 96mm plate. We can thermoregulate the storage, so we store samples, and we can actually have different temperatures for the exposure unit as well. So we can vary the temperatures if necessary. The capillary is automatically washed by the robot. So we flush with Helminex and ethanol initially, then we flush that out with water and followed by compressed air. And our measurement sequence actually would normally be to wash the capillary, to measure the buffer, wash the capillary, measure the sample, more washing, more buffer, more washing. This really allows us to keep the capillary clean, to stop fouling. So we can just keep on measuring all day without having to worry whether we've actually got a dirty capillary. By measuring the buffer before and after the sample, again, we can actually check that these are varying before and after the sample, and actually are varying through the day as well, to see if there is any fouling or build up from fouling, and then we can monitor this and change it as necessary. But this then allows us to measure actually up to about 350 samples per day, and I think we're going to see if we can actually try and optimize this a little better to get this over 400 samples over the next few months. Our other sample environment is our HPLC. So this is for SAXS. So essentially here we run the same sample, but we run it down one of these columns. These are either filled with polystyrene beads or silica beads. Essentially, this separates the sample out by size. So the larger samples come off earlier than the smaller samples come off later. This allows us to get rid of any aggregates in the peak and gives a more homogeneous solution. Again, we require about 20 to 100 microliters sample. We can do about 40 samples a day with the column, because the running of the columns will take a little bit longer. A normal GE column will take about 40 minutes to run. We have specific HPLC columns, and for these will take about 15 to 20 minutes to run these. We also need to equilibrate these, which takes maybe up to an hour to equilibrate. And we supply the specific HPLC glass vials. Again, we have the same storage and exposure, but we can actually also put these columns into storage as well to cool them down only to about 8 to 20 days. Here's the column in place. Our latest addition is we've created a new sample exchange unit, the 2V, and this was in collaboration with the EMBL Grenoble and the EMBL Hamburg. So this essentially is a vacuum compatible XYZ stage. If you look inside, we've got this piezo stage here, and then we have a mirror for the camera backlight, and the mirror's actually got a hole into it to allow the X-ray to go through, and then we can mount many different things on this platform. Anton Popov, EMBL, former ESF postdoc, he's been working a lot on our microfluidic suite of cells. So he's redesigned the new platform to actually to encompass and hold our microfluidic chips or devices in place. And we've got a few different devices. The first one's our gel cell. So this is it sat in place, and we can mount several different viscous samples or gels. As the robot and HPLC or both work on liquids only, this gel cell actually then allows us to expand the experiments that we can do. So we can actually then measure highly viscous samples or maybe hydrogels. We also have our mixing cell or our mixing chip. We then connect up to syringes as well, and these will then go into our into the vacuum chamber and plug it into the sample. And if you actually zoom in on this, you will see we've got the mixing cell actually has the buffer or the sample comes in, and then these has a little 3D mixing. You can just three 3D mixing cells before it actually comes out completely mixed, and then we'll actually measure through here. You'll notice there's no actual window material. We can actually measure the X-rays straight through this 3D printed method-related resin. This was originally designed by a master's student and then two students we had, and then Peter van der Linden, PSM, finalized this, and Antonio Callier, one of our postdocs, actually carried it in all our syringes to get those to work in bliss. So what does the data look like on this? So we managed to measure just simple BSA to start with. So we were measuring a buffer, and then we put on the second syringe, and then we can automatically mix in the BSA. And then we did a little bit of single value decomposition to actually work out which is buffer, which is sample, and then did quite a simple buffer structure curve. And this is actually very nice data because we're collecting just at 50 millisecond frames. Normally we'd actually collect at 1 second frames, but here we've got about 50 millisecond frames to get really nice data on a 5 mg BSA sample. We've also been able to do a titration as well, so we can actually just changing the buffer in steps, and then we can actually then take the sample, the frames from these steps, and then subtract them. And it's a little noisier because we're now taking 25 millisecond frames. We can actually see we can actually measure all the steps. So we can envision using this as like a time-resolved SAXS experiment, maybe ligand binding experiment, and actually seeing structural changes in the 10s to 20s of milliseconds. Or we can actually maybe change pH or salt concentrations, and maybe see phase separation or liquid phase separation happen in real time. But having just a really nice Beamline isn't enough these days to get really good high throughput. Beamline, we actually need really good software, and so this has been redesigned by Jean-Baptiste, who's working with us. So he coded our Beamline control in this BioSAXS-Q3, and we have a different page for each of our sampling environments. So this is the sample changer. As you can see, we've got the same layout as we have in the robot, and all the users need to do, they just need to click where the buffer is, and then they just click where the sample is, and then they just link the sample to the buffer, and add it to the table. And then they can just press, once they've put all the samples in, they can just press run. And they'll simply then, we'll just run through the samples, measuring buffer, sample, buffer, sample, buffer. We've got a queuing system as well, so we can just add these to the queue, and then we can just like queue up many sets of samples. We've also got a very similar screen again for the HPLC. Again, we just click where our sample is, give it a name, how long it's going to take, add it to the table, and press start, and it'll just run the HPLC. And we can easily change between sample changer and HPLC. It's just a simple valve click, which the BioSAXS cube will do. And we've also now started to put our SU2B in as well. So these are our syringes that are already coded in, as well as our XYZ stage. And now we have like different tabs for different devices and chips that we have. But that in itself isn't enough. We've also developed a automatic pipeline to analyze the data. So this is a FreeSAS that was developed by Jerome Kiefer. So this radial integrates the detector, and then we do a similarity matrix to see whether the buffer frames which are similar to each other, and the sample frames are similar to each other. So if there's any radiation damage, we can throw out those frames, and then we do the subtraction. And so this is a subtracted curve here, and then we'll also work out our standard parameters as well, size and shape and molecular weight. And these then, this is in SilkSview, but we also deposit this into our web-based iSpy-B, so XE iSpy-B. And so you can see here the samples going through, we're getting, let's say, the RGs and the Dmax volumes, and we've got our scattering curves, cracking plots, this PRR plots, and our Guinea regions as well. And then all this data can be downloaded in there by just pressing these download buttons, and that gives you just the 3-column ASCII files that most of our SAXS users use. But we're now moving away from iSpy-B, and we're moving into our data.ecrf.fl. So this is been progressing really nicely, and so now we can see we've got the curves for our buffer, our samples, and our buffer again, and we've got again many of the parameters that we want to see, and we also take photographs of the capillary to see whether the actual sample was in the buffer when we were measuring it as well. So really nice, clean format for our users. And again, you can just click these little 3 dots, and then you can download the ASCII files for its use. And this obviously is an online program, so we can download those. Users can download those when they get home. So this then leads me to our future plans. So our postdoc, Hayden Fisher, has been working on SAXS. So essentially what we want is that we want our users to actually give us the protein sequence before they come. And then we will actually generate an AlphaFold model for them. And then when they come, they put the protein name into BioSAXS Cube. We'll collect the BioSAXS data, and then we'll automatically fit the model from the AlphaFold with the SAXS data. And then, if in good agreement, we will present the model, the confidence metrics, and the deposition files. But if it's in a poor agreement, then we'll actually run it through some refinement programs to actually to refit the data. And so you can see that done here. So this is lysozyme, standard protein, but the AlphaFold model directly just gives us a chi-squared about 5. Actually, after refine, get that really nice chi-squared fitting about 1.46. to the BSA dimer, we can actually get this chi-squared right down from 53 down to 1.8. And this is just like moving the domains slightly and then fitting those back to the SAXS data. So that hopefully this will go in. This is going to go into EWOX, and this should be during this summer be implemented into our pipeline. So our users should be looking to be using this come September. We'll then actually add a different refinement process using Carbonara. So this is originally development calibration was done in Edinburgh and Southampton, and Hayden, the postdoc, was actually at Southampton before coming to us, so he worked on this when he was at Southampton, and also this was with Dynamics as well. And so this is using method dynamics and coarse grain method dynamics to actually help refine models to data. And again, we'll include this into an EWOX package and then into our platform. The last thing I'm going to talk about is we're hoping to actually get a wax detector to upgrade this. And so we can actually then do in situ SAXS wax. And we want to put the wax detector actually in a vacuum chamber as well. So again, keeping the whole the whole environment within vacuum. But why would we want to do that for proteins? Well, actually having the wax would allow us to probe more local secondary structure variations. So this will give us a little bit more about changes of the structure in solution and the dynamics for folding studies. We can actually do more protein ligand and protein interactions. And so this will actually allow us to see more smaller conformational changes that only detectable via wax rather than the normal SAXS regime. And we can actually see shifts in groups as well. Plus, we've had a lot of interest from these new RNA vaccines, such as like the COVID-19 vaccine, which is like a lipid nanoparticle with the RNA inside that. And so actually when we look at that with SAXS wax, we'll be able to actually see peaks and the specific peak of the RNA within the actual wax regime. So having the wax would actually help us to increase the different types of experiments that we can do, and would even maybe let us to do like fragment screening as well, or at least more protein ligand interactions. That just now just have to acknowledge many people that have been helping out on the Beamline for many years. So obviously our team, Jerome and the data of this, and Marcus, the BioSAXS, as well as our engineers, and so if you want any more information, just please contact Petra, myself, or Hayden, and please visit our website's complement links, and click here if you want to apply for any time. Thank you.